Hello class, welcome back. Let's take a look at net forces. In this video, we want to be taking a look at if we have a net force, what's actually happening. So of course we will need a free body diagram. We will need to look at what's happening along X and Y and any kind of forces, any motion that is happening, and we're particularly focusing on the forces here. So we're going to have to look at what our angles of motion are, and then we're going to want to resolve any forces along X and Y using our trig functions. And then once we know all that, what we need to do is also ask ourselves what's happening with X and Y forces. And since we know forces occur in pairs, and that means we have to essentially resolve a net force on X and a net force on Y, and anything that's left over will basically be what we call our resultant force, and which will be the direction that the force is applied, which would then translate into the direction of the motion for the object. So let's just jump in. Let's just go ahead and get ourselves a square here, just to represent our object. Typically squares and circles, remember, for our free body diagrams. So remember, we know we have a normal force and we have our force due to gravity. Remember the normal force being perpendicular to the horizontal planes. In this case, the normal force, you can see that is perpendicular to the plane. And then let's just say we're going in this direction and we say that it's being pushed or pulled in that direction. That would be our applied force. And opposing that obviously would be some sort of frictional force. And so we look at this and we realize that we have a force along X and we need to figure out what that net is. And so along X, we see that we have an applied force and we have our force due to friction. On the y-axis, there's also a net force because we have those pair of forces, right? And so we have our normal force plus our force due to gravity. And there's a tendency to write the opposing force secondly, typically because remember we set our coordinate system of X and Y, and typically that opposing force will be in the negative direction that we've assigned our coordinate system. So typically what happens is it's a lot of times it will be subtracted from it because it's in an opposing force, so it will have a negative value. All right. So let's go ahead and look down a little bit at another. Let's take this and go a little further with it. All right. Let's think about this. If we're going, let's just say we've got a pulling force. All right, let's just say we have a pulling force. That would be the force going up, and we would call that a tension. We would call it a tension force, and it is opposing the force due to gravity. Now, I'm not drawing this from the center, but remember, we're essentially drawing everything from center mass. Those arrows that represent that ray are that vector are basically pulling from the center. Okay, so we would have a net acceleration that we know is upward, and so we know we would have a positive net acceleration. All right, so we would have the force along Y net would equal the force up plus the force due to gravity. We know that our acceleration along the x-axis is 0.0 meters per second squared since it's not moving in that direction, and that lets us know that the net force along the x-axis also has to equal 0. Okay, so that's everything that we know just from the basic concept of looking at this particular problem. Just the concept of it's only moving upwards. How would we resolve those pair of forces based on what we know with motion? All right, let's take a look at something else. So we typically don't just push or pull things straight left straight right, straight up, or straight down. We typically tend to pull things at angles. And so we know we have our normal force. We know we have our force due to gravity. And keeping with the theme, we're going to say that this is the opposing side for our x. All right. And so we're going to go in this direction here, and we know that this is our applied force. Now, keep in mind, remember that remember you learned that you can take any sort of the line, and you can move it vertically. You can move it horizontally. Parallel. Forgive me. You can move it parallel along an axis, and it retains its value. I don't care if it's if you were drawing it that way, or if you drew something straight up and down. It wouldn't matter. We could take this and move it to this side here. It would not make a difference. It still has the same value, right? Knowing that, what we can do is, if by chance this thing right here were being pulled, let's just say it's being pulled in the direction that we show it being applied. Well, that means that the center mass is basically being pulled, and it is being pulled at some angle theta. So what that means is I don't have to draw this here. In the spirit of what we just talked about, I can draw it right there, because remember, we can move these lines, these vectors parallel, and they retain their value. So right now we can see here that we have the makings of a right triangle. So what that means is we're pulling at an angle. So here's our applied force. All right, now this is our applied force, because we're not pulling exactly straight. We're pulling at some angle theta. Oh, need two P's there. And that means we have a force along the x and a force along the y. And so this applied force, the applied force is our resultant, right? So now what we do is we just go back and we just start doing, I like the yellow. We're going to stick with the yellow. And we just start doing what we know about with our trig functions. Well, we know that the sine of theta, sine, so remember we've got SOHCAHTOA. So sine would be the opposite over the hypotenuse. Well, in this case, opposite of theta is the y, is the force acting on y. And the hypotenuse in this case, we know, is the applied force. Okay? So to resolve the force along y, we know that it would be sine theta times the applied force. And we are done. This right here would be how we would resolve the force on the y-axis. Okay? This is how we would resolve the force on the y-axis. So the same is true for the force on the x-axis. We just have to ask ourselves, what trig function will support this? So if we look at the cosine of theta, cosine, the adjacent over the hypotenuse. So adjacent is the force on x, the hypotenuse again being the applied force. So we could say that if we were to resolve for the force on the x component of this motion here, it would be the cosine of theta times the applied force. All right, so this and this, are examples of how we would actually resolve our motion. All right? Let's take a look at this more as a whole. Okay, let's go to another page here. Let's recap. We've got the force on X, and there'll be some net force, and that will obviously be the sum of the forces on X. And so there can technically be more than one force acting on that particular plane. So if we think about it, you could have, let's just say you had multiple ones. Well, there was a force, the first force on X, plus the second force on X, plus however many more there are there. So that makes sense. Then we've got the force on Y, and we will have a net. And so the sum of the forces on Y, again, well, we could have more than one. So we're just showing here that there could be multiples, but all of them together would equal that. And so the net force, as we know, the overall net force would be the sum of the forces on X plus the sum of the forces on Y, essentially. But as we saw, what we have to do is this right here does not account for angle theta. So that's why we go back and we use our trig functions. We resolve each individual component. And as we do that, we start to get something that looks a little more sound, and it's going to get us some nice, precise data. All right, or some nice calculations from our data. All right, so go do some practice problems, and I will see you in another lesson, and we will talk soon. Go do some of those practice problems, and I'll see you in class, and I look forward to answering your questions.